Hello students, sorry I couldn't be here today. Unfortunately I'm not feeling very well, but hopefully this video will give you an idea of what we're going to learn today anyway. So by this point hopefully you found this in the worksheet I've emailed out to you. So we've got a table here talking about ways to connect computers in an office with the cheapest cost. Anyway, so we could draw this table into a graph like this. Now, note how they're not listing any redundant connections. So what do I mean by that? Well, it says here A is connected to B, but it's not saying B is connected to A. Obviously, with computer cabling, the direction of the flow doesn't matter. So what that rather than just have 45, 45, 70, 70, they're just not writing it twice because that would be redundant. So B is definitely connected to A, C is definitely connected to A, D is definitely connected to A, as we can see up here. They just haven't bothered listing it twice. And there's nothing saying we can't do that. Anyway, so if we were to draw it, we would get something that looks like this, which as you can see is pretty cluttered. As A is connected to every single vertex, and as B is connected to every single vertex as well, we end up with something that looks very, very cluttered. It's non-planar, we have overlapping edges, it's very hard to read. Now look, it's certainly possible to solve the question this way using Prim's algorithm, but it might be a better idea to do it straight from the table. So what do I mean by that? Well, from the table here, what we do, let's first have a look at vertex A. What is the cheapest way to hook up A to the network? Well, clearly it's to connect it to vertex B. Then I move to the second row. So what I do is I scan across row B, and I also look up and down column B for the cheapest connection. So up and down column B, across column B. So I've already got this connected up, but what's the next cheapest connection? As we would do in Prim's algorithm, we're connected to the cheapest unconnected vertex. So it looks like the cheapest unconnected one would be vertex D. Then I move to row C. So I look up and down column C and left to right row C. What's the cheapest way to do it? Connected to vertex F. Then I move to the next row. I look left and right on row D, up and down column D. What's the cheapest way to do it? Connect to vertex E. Then I look at row E. I look left to right row E, up and down row E. What's the cheapest way to do it? Well, we don't need to connect up to vertex A again, and it looks like we're already connected to vertex D, so I'm just going to leave that one. And lastly, what's the best way to connect to vertex F? There's no way to do left and right here, so I just look up and down. It looks like vertex F is already connected. Might not be right though. Let's see what happens when we draw this. So we know A is connected to B. We know B is connected to D. We know C is connected to F. We know D is connected to E. And yeah, the network's not quite connected, is it? So let's flip back. What's the cheapest way to connect C or F to the rest of the network? Probably this one here. D and F can be connected with a connection of only 55. So I would do that. So as you can see, I end up with a minimal spanning tree that's a little bit neater than what we have here, but still the same answer. A is connected to B, B is connected to D, D is connected to E and F is connected to C. As you can see here, A is connected to B, B is connected to D, D is connected to E and F is connected to C. So look, it is a little bit of a fiddly algorithm. It took me a while to wrap my head around it, but it is quite a time saver when you have these large tables, especially when they're really large like this. Having said that, drawing a graph like this, like we've been doing the last couple of lessons, is a perfectly valid way to solve the question, and you would get full marks for that in the test. But look, I just thought it was worth showing you a different way to approach these questions. Anyway, students, hope you don't miss me too much today. Good luck with the rest of the questions.